extreme values, or whether there's maximum minimum, and there's a mean value theorem. There's a little bit of theoretical discussion too, so that we can prove that increasing and decreasing property can be captured by whether derivative being positive or negative in the factored form. It gives you very concrete and solid conclusion. But there is no jiggling up and down in between these and that numbers, because we prove that using mean value theorem. If the derivative is positive, it's always going up. There will be no up and down. So that's good. But the secondary level of sketching the graph is concavity. Okay, this is a little more subtle than increasing and decreasing property. So here's a definition. We should write that definition down. Is, I think, in my opinion, is easier because they introduce the definition that is in terms of derivative. If you think about the definition of increasing and decreasing property, the very definition, it does not have any calculus or derivative statement. It's about inequality, whether f of a is less than f of b, right? It's just a very algebraic statement. Here, the definition of a concave up and down, as you read it here, it involves the behavior of a derivative value. So it's more a calculus definition. But there are definitions out there, concave up and down, defined in terms of more algebraic term, not like this in derivative term. So that makes things harder. So they start with the easier definition in here. So we straight talk about derivative values straight away. Right. The graph of function f of x is concave up on an interval, usually open interval, if the derivative is increasing, right? Not a function, the derivative is increasing. The graph is called concave down on then whatever open interval usually. If the derivative is decreasing, if f prime is constant, then graph is said to have no concavity. Right? That's interesting and probably easier to understand. Let's consider an example. F prime of x being constant. Let's say that was 2. What do you think the f of x is? Let's say f prime of x was 2 on that interval -1 to +1. What kind of function does it come to you? Function whose derivative is 2. That's the condition, right? What if f prime is a constant? Then graph is said to have no concavity. So I came up with a function whose derivative is constant, right? Then what is the function? An example of this function is 2 times x, right? All right. So I think what went through your mind is that 2x has derivative 2, right? But can you come up with a function that is not 2x, but is still derivative is 2? Maybe I can throw in pi in there, right? -1 into whatever, right? So 2x plus a constant, again, you're sure that derivative is 2, right? But my next level question is that can someone find a function that is not in that form 2x plus a constant, but derivative is still 2? Is it possible? The answer is no, and that's pretty much that statement, that semi-uniqueness of antiderivative. This is one that we can easily verify. Oh, that has derivative too, but it's a fair question that can someone in the next generation can find some weird function whose derivative is still 2, but it's not like that. Mathematicians prove that that cannot happen. So this is the only function. That is kind of the statement, right? So that's important. So what is the shape of this function, f of x equals 2x plus pi? The one word that describes the shape of this function? Line, linear, right? In terms of concavity, that's the right word rather than increasing, right? 2x plus pi is increasing function, but more relevant here to this term no concavity is this shape. By looking at this line like this, which is precisely what they're referring to, we say this has no concavity. It's just increasing, but has no concavity. That's that. The other two conditions are weird, but we're going to look at examples. All right. They have pictures. This is their picture for something. All right. I'm going to label value like we did earlier. This is a graph of y equals f of x, right? I am looking at, for example, x equals -2. Then I'm going to label m equals, right? So is m positive or negative? Negative. What is your rough estimate of that compared to the other one that we're going to do? Let's make it slightly different from the other one. Yes, I think this is a 10 units in here one. I think he's maybe right. I have to kind of, this is like 2 units, right? And 10 units in here. So I should really go just about, that's 2 unit. That's like 20 units. So I would agree that the magnitude is roughly 10, but you have to measure it carefully in that. But it's -10, right? Okay, -10. Because scale is different. Okay, that's that -10, right? That is the value of what? Functional notation. F, what of -2 is -10? What symbol does it go in there? F of -2 is not -10. F of -2 is roughly 20, don't you think? F of -2 is roughly 20. That's a graph of y equals f of x. What of -2 is -10? F of -2, what I was saying, is not -10, right? F of -2 is 20. Then what of -2 is -10? F prime, right? F derivative, the value of a derivative is the slope of the tangent line. Okay. Make sense? Okay. So the value at x equals -2, value of what? Derivative was -10, right? Next thing they're going to do is at -1. So what is that value there? Just compared to that, let's just make it easy. Does that look like? So what's the easy answer here? F is negative, still negative, right? Negative what number? Maybe just 5, something that is, you know, less steeper than that. Does that make sense? This is -10, rise over run. This is slightly lower. Hope that makes sense. All right, again, this is what of -1? F prime. All right, going from the left to right, -2, -1. Is this -10 to -5? Is this increasing or decreasing? From -10 to -5. That's what the value of a derivative is changing, right? Is this increasing or decreasing? Is it decreasing? Is it increasing? -10 to -5, increasing or decreasing? Increasing, right? Negative, m was -10 here, right? Here m is -5. The best way to not confuse yourself is write this thing down. Not just staring at it. It will confuse you in the next moment. It'll confuse you in the next moment. Write it down. -10, left to right, and -5 is increasing, right? So what is increasing? That's right. F prime of x is increasing from left to right, right? How about here at that value? What is m value there? M equals 0, right? Is that still increasing? -5 to 0, is that increasing? Yes, it's increasing. Right? How about here? Our easy answer to that m is +5, right? There, m equals +10. So from left to right, I hope you agree, the value of a derivative, the slope of the tangent line as a number is consistently increasing all the way, right? That's what they're saying there. F prime of x, the slope is increasing from left to right. If that happens, what do they call that property? Concave up. This entire thing is concave up, right? But the function value is something different between in here. In that interval, what is a good description? It's concave up and function is decreasing, right? But here, the function f of x is increasing and still concave up, right? Yeah. So concave up can have these two properties. Decreasing concave up, increasing concave up, right? How that make sense? Yeah. And then the other picture is concave down picture they have is this one. Again, the best way to explain this thing to yourself is labeling it. Here, always from left to right. That's the key. What is the slope here? M equals, compared to that, we're going to say positive 10, right? And here, that value M is positive 5. And here, what is M value here? 0. At that value there, M is negative 5. And here, M equals negative 10. Now you wrote those numbers around that curve from going from left to right, clearly see, oh, the numbers I wrote down is always decreasing. Therefore, we call this one concave down, right? And here, the function is increasing but concave down. Function here is decreasing in the second interval, but it's still concave down. So concavity can be mixed up with any increasing and decreasing property. Make sense? So I use this x to the n to show the different levels of concavity. These are all concave up or concave down, these three graphs. Number 1 and number 2, number 3, which one is concave up? Is this one concave up everywhere? How about the second one? Is that concave up? How about the third one? Is that concave up? Yeah, all of them are concave up. But something is different, right? That level of difference is something what's called the curvature, and you learn this one in detail in Calculus 3. Right now, all we care about is just rough shape. All are called concave up. All are same divided into, decreasing and increasing around the symmetric point. And this one in here is all concave down, right? But it's extreme. This is like y equals x squared. This is x to the fourth, probably. This is x to the sixth. They all have this type of graph. It's different type of concavity. And here's an animation to show you that the concavity can be mixed up in all the increasing manner. Right now, the function's increasing here, right? But I'm going to slowly change the concavity here. So the concavity, it has no concavity because it's straight line. But I hope you can see that. Slowly, it's bent around like that. And here is concave down, right? If I just sample that, you will say that's probably concave up, right? Still is going up, all rising, but you can mix up this concavity within that increasing interval, not just have to be separated. Oh, here's a decreasing, increasing. That's really easy to see, but as you just keeps increasing, you can still mix up the concavity up and down in here. Does that make sense? Yeah. If I go further, the bent around further, it begins to actually have decreasing in here, right? And then concave up. And here's increasing, but here's decreasing again, things like that. So same thing goes down here. Start from all decreasing at the beginning. It remained decreasing and beginning to have, slight concavity change. This is still remaining decreasing, but it's a concave up here and concave down, right? Just to show you an example of keeping the increasing property, you can still change the concavity up and down. All right? An extreme example, they will sketch it like this. And here, f prime is positive, it's increasing, right, from the analysis. If you can still factor, if you can see the second derivative is negative, then it implies that the first derivative is decreasing. So it's concave down, things like that. But because we saw the example, increasing and concave down and decreasing concave down, that part, I think it's easy to understand. So here's a statement about that second derivative. The very definition of concave up and down doesn't have a second derivative in it, right? But now it has a second derivative in it, and it is not the second derivative test. So please not get confused by it. It has a test for concavity, that's the name. It has second derivative in it, but it's not the second derivative test. So let's write this one down. Test for concavity. FB twice differentiable on the interval if the graph is concave up, if the second derivative on that interval always positive, it's going to be concave down if the second derivative value is always a negative on that interval. It's an important thing that you will be using all the time to conclude the graph is concave up or concave down. Something is positive and something is negative, just like the first derivative test. And maybe you can write down a note next to it, this is not the second derivative test. This is not. But it's called test for concavity. That uses second derivative, right? Positive and negative sign of second derivative. All right. Can someone tell me what the definition of a concave up was? If what satisfied, what do we say is concave up? Anybody remember? Derivative is increasing. That's right. Thank you. Is increasing. Can someone increasing on that interval I? Can someone relate that this very condition to this new condition they're saying? If this is true, seems like they're suggesting if f double prime of x is positive, they're suggesting this is a satisfied, therefore we can conclude it's a concave up, right? Can someone explain why is this second derivative is positive? Therefore, I can conclude if let me say that again. If the second derivative positive, why is it, f prime of x is increasing so that I can conclude it's a concave up? So this is given. Second derivative is positive on that interval. Why is f prime of x is increasing? Something being positive and increasing. That's what we've been doing before, right? Right. So what if I write it like this? F double prime of x is really first derivative of what function? F prime of x, right? And they're saying this is positive, right? If derivative of some function is positive, what is the conclusion we have about that function? No. If this derivative of this function is positive, what immediate conclusion do we have about that function? What is increasing? That inside there is increasing, right? So that's correct. If I'm looking at this function, whatever that is, its derivative is positive by the first derivative test, right? This is increasing. Isn't that right? Here's whatever the function I differentiate is a positive, is increasing. That's exactly this condition, right? By definition of concave up, is that. If the derivative is negative, you can interpret it again like this. That means the first derivative of the first derivative, derivative of the first derivative is negative. Therefore, the first derivative is decreasing. That is the very definition of concave down. So I think it's really easy to understand this test for derivative. Does that make sense? No? Yeah. How about this sentence? Is this still confusing? Yeah. Okay. How about this one? Isn't that the same statement? F prime of x is increasing. F prime of x is increasing. But the very definition of concave up is f prime of x is increasing. Okay, that part. So f double prime of x is d dx of f prime of x, right? That is negative, right? Then what is the conclusion about that function? We just differentiated one time. F prime of x is decreasing, right? Because the function's derivative, the first derivative is negative. The derivative of the first derivative. Confusing. Anyway, so that's the very definition of concave down. So let's practice together. If this is my f prime of x, I call that one C1, C2, C3, C4, C5, C6. All right. Can you come up with a one interval the function is concave up? So this is a graph of f prime of x, right? Just like before. On what interval, on which interval, something to something, f is concave up, let's say. C1 to C2. C1 to C2, that's what we're looking at, right? According to the test of a concavity, what is it we need? Right. That's all right too. Is f prime of x is increasing in here? This is f prime of x, right? Is this increasing always? This is decreasing here, right? Not f of x. F prime of x is decreasing, right? So that must be up to here is concave down, right? If the f prime of x decreasing is a concave down. How about here? F prime of x is increasing, right? So it's a concave up. So I should call that one maybe D1. So C1 to D1 is concave down, right? So concave up must be D1 to D2, D1 to C2. Do you agree? Yeah, D1 is here, somewhere in the middle, and C2 there. The function here is increasing, correct? But what is that function we're looking at here, graph? F prime of x. F prime of x is increasing. Therefore, what is concave up? What goes here? What is concave up? No, that is concave up on that. But what is concave up? Not f prime of x, f of x. We're concluding about f of x by looking at f prime of x. So f of x is concave up there, right? Can you come up with a concave down then? Somewhere over here, right? Yes. This, yeah, f prime of x is also concave up, but that's not what we're concluding about it. F of x is concave up, right? Not because the shape is concave up. This is not f of x. This is f prime of x, right? Was that your question? You said about D1 to C2, right? That it f of x is concave up. But it happened that the shape of this f prime of x is also concave up, the graph. But that's not why it's concave up. Yeah. Can someone come up with that last one there? Somewhere else is concave down. C5, C5 to D5. I'm going to show the D5 here. Somewhere in the between. D5, right? That's probably what you're thinking, right? So why is it concave down? It looks like concave up, right? Right, it's decreasing. F prime of x is decreasing there, right? So C5 to D5, f of x is concave down because f prime of x is decreasing. Okay? Yeah. Time's up. So we'll continue not tomorrow.